Even if the sky is falling down, even if the sky is falling down, yeah. The sky is falling down.
And welcome everybody. Hey, thanks for joining me. I'm glad that you are here. For those of you who are brand new to this channel, my name is Keith Barker. Glad to have you. I was looking at the queue. I see a lot of familiar faces. We are going to focus on another CCNA topic, and this one is going to be OSPF, Open Shortest Path First. And we're going to get right into it. And the challenge today is to have a plan, configure OSPF, and then verify OSPF. And if we have hiccups or problems along the way, it'll give us the opportunity for you and I to troubleshoot those together. So let's go ahead and bring up the topology here. And here it is. I worked for minutes on this. So here's our topology. Let me explain it to you real quick, and then we'll go to work configuring it. And one of the benefits that we may discover as we plan this and configure it together, if you're brand new to OSPF, it'll give you a good idea how it works. And also, if you've seen OSPF before but thought, oh, what's this or what's that, there may be some insights as well. We are going to focus on single area OSPF, which is part of the requirements for Cisco CCNA. And that's for 200-301, their Cisco certification. All right, so here we have 4 routers 1, 2, 3, and 4. And we've got some connections between them. We've also got this switch. It's a layer 2 switch, so it's got some access ports connecting R1 and R2 together. And then there's a PC hanging off of gig 00 on R1. It's actually going through a switch. And then off of R4, there's a switch that goes to a PC over here. And there's your IP addresses. So, I love creating network topologies when we're learning and practicing things that are pretty easy to interpret. So we're not getting lost in where's that network or where's that network. Let me show you how easy this is to decode. So these routers, I use the 10.0 network for everything. So we are going to make a single area for OSPF. It's going to be area 0. So all the routers, all the networks on all these routers are all going to go into this giant area called area 0. And the benefit of areas in larger networks, think of it like a room with 100 people in it. And if we had a room with 100 people and then we were asked, okay, you're going to get a little bit of information from every single user, every single person, and you have to keep that all in a database and remember all of it, that's a lot of overhead. So in OSPF, to make it more manageable, we can carve our network up into smaller chunks. Maybe we have smaller rooms. It's like having a room of 10 people versus 100. And then all we have to do is just memorize the people in that smaller room, and it's less to manage, there's less in our database, and it's easier to calculate. So that's the benefit of having multiple areas. So in our topology, we're just going to use one area, and we're going to put all of our, it's like a one room, we're going to have all of our routers sharing all their routes with everybody else in that same area. And in this topology, 10.0 is going to be the first 2 numbers of all the IP addresses. And then between routers 1 and 2, it's going to be 1 and 2. I just put the 2 numbers together like X and Y. So this network is 10.0, 12. Between R1 and R3, it'd be 10.0, 13. Between R3 and R4, 10.0, 34. And I just put in there so we could, when you see a route, you'll say, oh, that's what that is. Also, each of the routers, their last octet, the last number of their IPv4 address, I'm using the same as their router number. So R1 is going to be .1 on all of its interfaces. R3 is going to be .3. R4 is going to be .4. And R2, .2. So in this topology, I've got all the IP addresses already configured, so we can focus right on OSPF. So let's make a plan for OSPF. And here's what I propose we do. We'll have all the networks in area 0, which means all these routers and all their interfaces that will tell them that any networks are going to be in area 0. And let's include every interface that begins with 10.0. We want to put that into OSPF. Now, we had a separate stream on network statements and wildcard masks. And so if all of these routers, if we wanted to add any interfaces that start with 10.0, which is all these Ethernet networks, the network statement would look something like this. Network 10.0, and then we follow it through with 2 more octets. So 1000, 10,000, a space. And then if we want to match on these first 2 octets, these first 2 numbers, what we do is in our network statement, we'd say, we care about matching on the 10 with a 0. A 0 for the wildcard mask says we care about matching on the second number. And then for the wildcard mask, I'll put these in a different color. That'd be better. So the wildcard mask, let me go ahead and grab, black. Like, I don't care what they are. I'm so dark. So a 255 in the wildcard mask says, I don't care what that third octet is. And a 255 here in this last octet means I don't care what that last octet is. So what this means to the router is, okay, I get it. I'm going to look at all my interfaces, say the router, and I'll look for any interfaces that begin with 10.0. And if they do, boom, I will have those interfaces participating in OSPF. I hate that term. Any interfaces that match 10.0, what it means is those interfaces, whatever networks they're connected to, those networks are going to be in OSPF. And if there's a neighbor, like another OSPF router, off of one of those interfaces and we see their hello messages back and forth, we can become a neighbor with those and start sharing information with them as well. That's what it means. So that's how the network statement works. And then we're just going to specify that we are going to put these into area 0. So that's our plan right there. Boom. So, oh, one more thing. Let's go ahead, and each of these routers has a loopback interface. And it matches the router number. So router 1 has a loopback of 1111. And router 2 has a loopback of 2222. So if we don't, got a question for you. If we don't specify the router ID in configuration mode, we don't go in and say router ID is this or router ID is that, what ID is the router going to use for the OSPF router ID? And if you know this, I'd like you to think about what that is. If you're not familiar yet with what it's going to use, here's the pecking order. It's 3 things. My finger no longer hurts. I smashed it in a door a week and a half ago, but no longer hurts. Hopefully I'm keeping the nail. So I'll give you this side. I'll give you the friendly side. So there's 3 things it's going to use for the router ID. If you have the router ID manually configured, it uses that. If there is no router ID manually configured, the next thing it's going to use when OSPF comes up, it's going to go when it starts, it's going to use the IP address on the highest IP address numerically on any loopback interfaces. And if there's no loopback interfaces and you haven't configured the router ID, it then says, okay, I'm going to take the highest IP address on any other interface, like a physical interface. And that's what it uses. So a router ID is in dotted decimal format. It kind of looks like an IPv4 address. However, it doesn't have to be. I mean, you could use like 250.5.5.5. It doesn't care. So even though it kind of looks like a dotted decimal address, it just happens to be represented the same way with 4 numbers, 3 periods, and that's the router ID. All right, so as far as our plan goes, because I have loopbacks on all these, I'll just go ahead and let those loopbacks, because it's the highest IP address, it's the only loopback. The router ID will automatically be 1111 for R1 and 2222 for R2 and so forth. So great, that's it. Let's go ahead and implement this plan. So let's start on R1, and you know what I'm also going to do? I'm also going to do what I would do in a production environment, unless I was using network automation, which would be even faster. But if I knew my configs and I had an idea what I'd probably use Notepad or some text editor, put the commands in, verify them, and then just paste them in, especially if they're very, very similar. So let's do that as well. Let me go ahead and clear the screen. And let's go ahead and get to the lab and make sure it's up. And hey, it's still responding. That's great. All right, so I'm going to bring up my favorite tool, one of my favorite tools. I have a few. Notepad. And so we're going to just go into each of these routers 1, 2, 3, and 4, go into configuration mode. And let's see here. Let's do a view and format. Let's do this real quick. Format, font, and let's go bigger. That way you can read it with me. There we go. Easier to read. Good. So config T, and then we're going to go to router, OSPF, process ID. I'll use 1, and then we'll simply say network. I just tabbed that out. In a Cisco router, you tab it out. It gives you the whole command. But here it's saying, Keith, I don't know what you mean. So I will spell it out here so we can see it. So the network statement is going to be network 10.0.0.0. And we care about the first 2 octets So the wildcard mask would be 0.0, which means I care about the 10 and the 0 matching, but I don't care about the third octet, says that 255, all bits on, and I don't care about matching on the last octet. That means the third and fourth octet on this router's interface, once we apply it, could be anything, doesn't matter, as long as the first two numbers are 10-0, it's going to match. And then we're going to put any networks that match that into area 0, just like that. And I think that's it. We could paste this command on all 4 routers and it would work. So let's I'm going to copy that. Just going to highlight it and right click and copy it into my buffer on this local virtual machine that's running this lab. And I've got a question for you before we apply this. If you've been with me for a few of these streams, you probably know that I'm a big fan of verifying what device we're on with a simple show command before we start plowing in or pasting in configs. So I'm going to strongly recommend that again here. Just verify that we're on router 1, that the interfaces that we think should be there are there before we start configuring. So in our topology, we're expecting R1 to have this interface 1/0 and 2/0 and 0/0 with these networks 10.1, 10.12, and 10.13. So let's just quickly verify that, sanity check to make sure that's the case. So we'll do a show IP interface brief. And sure enough, there's our 3 interfaces with those respective IP addresses, which is great. And then I also have a loopback down here. So I'm on the right device. So so I got a mistake I just made. I highlighted some text in the CLI. And as a result, when you highlight with most terminal emulators, it copies. So if I pasted now, I'd be pasting a bunch of those numbers. So I didn't go back to my text document and copy again before I paste. Oh, and by the way, I think I told some of you that I brought down a whole network once many years ago. And this is how I did it. I was in a config, I was pasting in something, and I had grabbed something else. 2 things. I was on the wrong device, and I had the wrong copy because I was highlighting something else. Anyway, nasty business. That mistake never happened twice in production. All right, so let's go back to Notepad. And here in Notepad, we'll copy that, and we'll go to R1, and boom. All right, that seemed painless. Let's do some verification commands because it's a 2-step process. Config and verify. So let's do a show IP protocols. So that verifies that Ospf is running. Here's the router ID. And here's the network statement that we just put in, saying that we care about these first 2 numbers, don't care about the last 2 for matching purposes, and any networks that match that are going to go into area 0. That looks good. We'll do a show IP Ospf interface brief. And that looks good too. Wait, the state is wait. Because each of these network segments are Ethernet. The default network type is broadcast. And default network type of broadcast is we're going to assume that we're using a designated router. So this router simply waiting, I believe it's 3 times the dead interval before it starts to go ahead and become the DR. It wants to make sure there's no other DR out there. So it's waiting for a moment, and then finally, because no one else is out there, it'll become the designated router for all 3 segments. Now, a couple things that happen with Ospf. In Ospf, there's a lot of data that's being shared. Now, if you only have one router, there's not a whole bunch of data, however, in Ospf, but routers generate what's called a router LSA. Now, link state advertisements are how 2 routers, let's say it's you and I, we're both routers, we see each other's hello messages, we send frequently, and we say, hey, we're on the same segment, we agree about the network, we agree about the area, let's become neighbors. And we can go ahead and start sharing our information with each other. And so each router creates a link state advertisement. And a link state advertisement, think of it like it's all about me. Not me, I'm talking, but the router would say this. Router 1 would say, it's all about me. Here's my link state advertisement. And in this link state information, it's talking about all my links. And it pulls out the details. It says, here are the details. I'm connected to network A and network B and network C. And those are the states of its links. Hence it's called a link state routing protocol. So every router is going to generate its own router router LSA, and it's also referred to as a LSA type 1. So if you ever hear of a router LSA or a LSA type 1, it's simply the router. I'm so happy, says Mr. R1. Here's a link state advertisement that I have. I'll put it in my database, and it has information on those 3 networks. So I thought, well, it would be cool, instead of just like hearing the theory about this, let's go take a look. I mean, router 1 at this moment is the only one running OSPF. So the Ospf database, think of a database like a collection of LSAs, and it gets pretty gnarly after a while. There's a lot of, if you have 20 routers, you're going to have at least 20 router LSAs, plus some additional designated router LSAs, network LSAs that come out too. So while we just have one router, let's take a quick peek at the LSA. And this is a handy tip because by building it step by step and learning the individual pieces, like starting with CCNA, which is the perfect place, it helps when you start getting to the professional and enterprise and advanced levels and expert level by having a solid foundation. So let's do that. How do we ask for that? Let's first of all do an up arrow key. So router 1 is now the designated router for each of its broadcast network segments. And that's because it's pretty easy to win when you have no competition. There's no other routers running OSPF yet. All right, so router 1 is the designated router. And if we do a show IP Ospf database, okay, let me show you a question mark. There's a lot of information that we could look at regarding the Ospf database, but think of it like this. Think of the Ospf database as a collection of all the LSAs that are being advertised and synchronized in the entire area. So if there's 20 or 40 or 100, all those LSAs collected on a router would be called the link state database. So right now, we should just have one. That's what I'm banking on. Let's take a look. So if we do a show IP Ospf database, I love it. Okay, so this is a router link state. Now, a router link state, if this was in English, it would say this. It would say LSA type 1, a router LSA, because that's what this is. So this router is in area 0, so this LSA is going to be found on every router that's in the area because we share. We have identical copies of the link state database. We advertise it with our neighbors and we propagate the information. But right now it's just router 1. So if we want to take a look at the details of that, here's what we would expect to find. What we would expect to find is that if we said to this router, hey, what's in your LSA? Router 1 would say, well, I have 3 interfaces. I've got 0, 0, I've got 1, 0, and I've got 2, 0. Make sure I got those right. Yep. And those networks are respectively 0, 0 is the 10.0.1.0 network. And 1/0 is 12, 10.0.12.0. And 2.0 is 10.0.13. Oops, let me, boing, 13. There we go. So, and they're all up at the moment. So if we looked at that LSA, that router type 1 LSA is literally going to show us that he's got those 3 links. Now, at the moment, he's the only router that cares because nobody else is running OSPF yet. But it's handy to be familiar with what to expect and also a quick way of how to see it. So let's take a look at the interface and take a look. So to do this, we'll just do a show IP Ospf database and then we'll type in router. And that's a fancy way of saying, please show me the LSA type 1s, which is the router LSAs. And there's only one of them, and this is it right here. This basically says that this LSA, this link state advertisement, was generated by the router that has the router ID of 1111, which is router 1. That's his OSPF router ID. And if we hit the space bar, which I'll do right now, and go through these, check it out. He's got 3 links. We're not surprised. We knew, right? We knew based on the interfaces that he had and the network statement that we used that he'd have these 3 networks connected. And they are the 10.0.13 network, which is the interface off, that's gig 2/0. And then we have the 10.12 network, this bad boy, and that is the gig 1/0 network. And then there's the 10.0.1 network, which is gig 0/0. So the cool thing is, by looking at this when you don't have 15 routers and lots of different LSA types flying around, it's a great way to help get your feet wet with the basics of understanding LSAs. And in CCNA, it's single area, so you don't have to worry about anything beyond that. And there's only 2 LSA types in a single area OSPF, as long as we're not doing redistribution, which is beyond CCNA. So the first one of those is a router LSA type 1 that we're looking at right here. Okay, so the next step that we are going to do, let me clear this off, is we need to bring up some other people to the party. So let's take a look at our topology, and let's go ahead and use those same commands, the configuration commands, to bring up R2. Now, it's interesting. I think it's really interesting when we bring up another router. So right now, it's like a prized possession. This is R1. This is my LSA. It's part of my link state database. It's the only thing in there because he's the only router. But once we have another router, let's imagine that I'm going to make this a carrier. So here's the link state database for router 1. So router 2 shows up and starts sending little hello messages. And those little messages are sent to a multicast address, but little hello messages. And router 1 says, oh, I see you over there. And I see that you see me. And they go through a process of states as they start to discover each other. And then if everything's lined up, meaning if they agree on what the network is between them, they agree with the authentication, like, are you using authentication? If you are, what's the password? Or if you're not using authentication, they have to agree on the network type. Are we going to use a DR or no DR? They have to agree on the timers, the hello interval, which on Ethernet is by like 10 seconds by default, and the dead interval is 40. So they have to agree on that. Assuming they do, they can see those in these little hello messages. They'll go ahead and start to negotiate, and then they'll say, hey, great, welcome aboard. Now, router 2, who just came up, doesn't know about this yet. He doesn't know about the link state advertisement from router 1. So what they'll do is they'll share. Let me get another cup. So router 1 and router 2, basically router 1 will say, hey, here's my link state advertisement, so you know all about me. And let's go ahead and use yellow. Yellow. And R2 is going to have its own router, LSA, type 1, talking about its links and what it has up and can reach. And it's going to have that, and it'll share that information over with, I'm tapping in the link states inside of the LSA. And it'll share that with R1. So at the end of the day, every router, did you say every router? Yeah. Every router in the same area is going to have identical copies of the link state advertisements. And the collection of all those is called the link state database. So it's not rocket science. They basically share information and make sure they're synchronized. And then once a router has all the details, it can then calculate from where it is in this topology. It can calculate its best path based on longest match and then metrics and so forth of how to forward packets. All right, so let's bring all that's to say, let's bring up router 2. So if we go to our lab, which I'll do, and go to Notepad, I think this will work. So I'm going to copy that. This basically says I'm going into configuration mode. I'm enabling OSPF. I'm going to use process ID 1. Now the process ID doesn't have to match between routers in the same OSPF area. It's just locally significant on the router. And then network 10.0.0.0 and matching on the first 2 based on what the wildcard mask says, and put those into area 0. So great. I will copy all of that. Right click, copy. We'll go to R2 and verify that we're on R2. Show IP interface brief before I paste this in. All right, so great. So R2 is configured. Let's take a look at the IP addresses. R2 should be connected to this network right here, which is the 10.0.12, the 10.0.24. It also has a gig 00 interface going to 10.0.2. But mostly 10.12 and 10.24 is 10.0.12 and 10.0.24 are what we're looking for. So I'll verify I'm on the right device. And sure enough, okay, so I'm on the right interface, right devices, and I will right click, and it's done. Da, 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 da. So in a matter of time, through the hello messages, R2 and R1 should discover each other, become neighbors, and life should go on. Let's go ahead and go to R3. From the topology, R3 is this bad boy right here. It has 2 interfaces in area 0, and maybe 3. It might have a gig 00 as well, but 2 that we care about, 10 and 40. We'll go ahead and paste the configuration there. So here we are on R3 and R4, same thing. And then we'll do a show IP OSPF interface brief. And great, so he's in a wait state. And after the dead interval, we can do a show IP OSPF interface for gig 2/0. So that command, show IP OSPF interface gig 20, will show you lots of really cool information, including, let me get my pin out, including what the network type is. So if the network type is broadcast, that means we are going to be using a designated router. If the type is non-broadcast, that also means we're using a designated router. And any of the other network types, point-to-point, point-to-multipoint, etc., they do not use a designated router. But so that's my screen moved on me. So it's good to know. That's how you verify what the network type is, and we can manually change that. Here is the hello interval and the dead interval. They have to match. If you want to be neighbors, they have to match. And based on these network statements, these console messages, we just went into a full state. Now, full means that we found each. Full means we found each other. Says R4 to R3 and R4 to R2. We found each other, and we agreed on all the parameters: the network address, the area, the authentication, and we got so excited about seeing each other that we shared each other's LSAs and we got updated copies. So now if we have 3 routers, let's go ahead and use it. If we have 3 routers or 4 routers in the OSPF area, once those neighbors get into a full adjacency, that means they have synchronized and have identical copies of the link state advertisements in their link state database. So what we should see is that on any router, once we're fully synchronized, router 1, 2, 3, and 4, that if we looked at the link state database with all the router LSAs, and now we're going to have designated network LSAs as well because of the DRs that have transit devices on them, they're all going to be identical. So the link state database, identical on all 4 devices. All right, fun times. Fun times. Now, let's take a look at, let's see our objectives. Our objectives, as I recall, were to plan, which we did, configure, we did, and verify. All right, so let's do some verification. All right, so let's go ahead and I've got a PC out here, PC1, and let's go to R4. Let's go to R4 and check a few things just to verify that OSPF is working. So here on R4, fantastic. A couple things we can do. One, show IP protocols. That shows you what routing protocols are running. Here's OSPF 1. Its router ID is 4444. Fantastic. As far as the number of areas this router is connected to, it is 1. It's in a single area, area 0. And here is the network statement, which says we matched on the first 2 octets on the interfaces, and those interfaces became part of OSPF. And we've learned information from the router IDs of 1111, 3333, and 2222. And that's because R4 has an exact copy of the full link state database, which includes information from R2 and R3 and R1. And if we went to R1, it would say, oh yeah, I have information I've learned through the link state advertisements from 2, 3, and 4, because they're all shared. So we have a neighborship, we share all the information we have, and effectively we're synchronizing the link state database on every single router. Okay, so testing, yeah. Like, where are you going now, Keith? Where are you going now? Let's go ahead and verify routes. How about that? Let's do a show IP. Before we do that, let's do a show IP OSPF. Press enter. And this is going to show us a lot of great details about OSPF, including the process ID again, the router ID again, a lot of stuff in here that we may not need right away, but it also shows us the number of interfaces in the backbone, which is 3. So area 0 is the backbone area. And here are some other parameters as well. This looks great. One aspect is this, though. Reference bandwidth unit is 100 megabits per second. Let me explain how that works. In fact, I'll just do it on the whiteboard right here. If we had a 10 megabit per second interface, that's Ethernet, and we use the reference bandwidth of 100 megabits, so there's 100 megabits and we divide 10 into 100, the result of that would be a cost of 10. If we had a 100 megabit network interface card and the reference bandwidth, which is 100, still is, and we divided 100 into 100, the cost is 1. And you know what? That was fantastic for like a decade ago, maybe more. But now we've got interfaces that are easy a gig. So that's 1,000 megabits per second. And so if we have the reference bandwidth of 100 and we're dividing 1,000 into that, that is a fraction. And here's what Cisco does. I'm going to round up to 1. So even though it'd be like 0.1, it rounds up to 1, and that means that OSPF by default cannot tell the difference cost-wise between a gigabit interface and a fast Ethernet interface. That's like a mistake of tenfold. So that's just a fact of the matter, and so we need to correct that as well. But I just want to make sure we have adjacencies and make sure we have basic route information, and then we'll tweak that if we need to as part of our troubleshooting. All right, so on R4 still, and here he is in the topology, just to make sure we're on the same sheet of music. We're looking at R4. And on R4, if we do a show IP in OSPF interface brief, one of my favorite commands, that's great. And what that's showing us is, let me clear that off, it's showing us that we've got these three interfaces, all in area 0. There's their interfaces that got them in, and so the first 2 octets are 10-0, and as a result, that's why these interfaces are in there. Their cost is all a cost of 1. They are all currently designated routers. Now, in OSPF, if there's a network segment and there's 5 or 6 routers on it, it would be a nightmare to do full adjacencies with all the routers with everybody else. There'd be a lot of redundancy. You don't need it. So instead, on a broadcast or non-broadcast network type, there's going to be a clearinghouse. It's like the King Kong of the network of that segment, and that's called the designated router. And the designated router is going to build full adjacencies with every other device on that network segment. And that way, you don't have to have, if you have 10 devices, you don't have to have 10 devices with full adjacencies and sharing all their information with all the other 9. You can just have them exchange information with the designated router instead, having a full adjacency between, they call it a DR other, but a non-designated router with the designated router. And there's also a backup designated router as well for fault tolerance. But that's how that works. So this router, because, now, why did he win? Well, he won on some of these interfaces. He became the designated router on this guy because there's nobody else out there. See, that means there's no other neighbors out there. No other OSPF speakers out there. But on these 2, he won the designated router role because he has a higher router ID. That's the reality of it. So when a router, when 2 routers love each other very much, but they have to decide, who's going to be the designated router and who's not. The one that has the highest priority on the interface is going to be the DR. Unfortunately, the default priority is 1. So that's the same on everybody. And if we went to 2, that would win, but the default's 1. So if they both are powered up at the same time, the one that wins the designated router role is going to be the one that has the higher bridge ID, all other things being equal. The other thing too is if a router got booted first, like it's running OSPF, it got powered on, then 5 minutes later some other router came up, the designated router doesn't give up his role. It's like, oh, nope, I'm it. I see your great priority, everything else, but I'm still it. So it's not preemptive. A new router coming up is not going to boot the existing DR out of his role. He's going to keep it. But if they both boot at the same time, and we installed OSPF pretty much at the same time, the one with the highest priority on the interface wins. And if that's the same, the one with the highest router ID. So router 4, out of all of our 4 routers, has the highest router ID. That's why I won. Okay, curious minds want to know. So let's next check and verify our neighborships. So we'll do a show IP OSPF neighbor. Won't you please, won't you be my neighbor? And I like doing these 2 commands in this order because this command right here, show IP OSPF interface brief, is all about me, says the router R4. So on these interfaces, I'm the DR, I'm the DR, I'm the DR. And when you do show IP OSPF neighbor, it's about them, the other device. So this output, show IP OSPF neighbor, is saying, okay, I've got 2 neighbors. Let's pick 3333, which is the router ID of R3, because that's his loopback that he used for the router ID. And my state with that guy is full, meaning that's a full adjacency. Think of a full adjacency as you share everything. So if my link state database is this, is all these LSAs from all over the place in that area, I'm going to share everything with them and ask for updates and communicate with them. That's a full adjacency. That's what that means. All right, and then this second part here means that that device is the BDR, the backup designated router, in case the primary designated router goes away sometime. And there is the interface that we learned about them on. Okay, so let's do some testing. I'm game. I think we've configured OSPF. Let's go ahead and do some testing. Let's go to PC1. Oh, we didn't do routes. I want to verify routes. I take it back. So let me take a look at the routing table. So show IP route. The whole reason for this is the routes. Show IP route, and we'll limit it just to OSPF. These are the OSPF learned routes. So R4 knows how to get to 10.0.1, 10.0.2, 10.0.3, 10.0.12, 10.0.13, and he's directly connected to 34 and 24, and that's why they're not showing up as OSPF learned routes. Okay, so that looks good. So let's go ahead and test a ping. Let's go to PC1, which is a little virtual machine, and let's do a ping from this address, which is 10.0.110, and let's ping over to 10.0.410, which is PC4 down here. So the network space is, I get my pen up here. There we go. So here's the network space. PC1 is on 10.0.1, PC4 is on 10.0.4. If you need any assistance with networking and subnetting, please join me for Subnet Saturdays, where that is the complete focus, and we'll bring you right up to speed on all that. Okay, so let's go to PC1, and we'll make that test. So I have a tab here for PC1, and here's his IP address, and let's do a trace. So on Windows, it would be, the command would be Traceroute, T-R-A-C-E-R-T. On Linux boxes, it'd be Traceroute. Yeah, and so it would also on Cisco iOS routers, it'd be Traceroute. So here on this PC, it's trace, and let's go to 10.0.4.10. That's the PC IP address of PC4, and I'm going to do a -P space 1. Now, Keith, why are you doing a -P space 1? By default, on Linux and Unix and well, the same thing, on Linux platforms and on Cisco routers, when they do a traceroute command to trace the path a packet takes through the network, here's how it works. They send the first packet out with a TTL, a time to live of 1. The first router sees it and says, oh, time to live expired, because every time a packet, layer 3 packet, goes over a router, it decrements the TTL, the time to live field. And so if you send out a packet with a TTL of 1, the first router kills it, sends a message back saying, I killed your packet. And you're saying, that's what I wanted. And so with Traceroute, we can send a few packets with a TTL of 1, and then a few more with a TTL of 2, which makes it past the first router into the second router. And that's how we're tricking the network. Sorry about that. That's how we're tricking the network to give us information on the path that the packet's taking through the network. It's just a trick. So with Linux and with Cisco iOS, it uses UDP at the transport layer. And with Windows, with Traceroute, it uses ICMP. So the benefit of using ICMP is that it just looks like a ping request to the destination device instead of some kind of looking for an unknown port that it's not listening on. So what I'm doing here is I'm just telling Trace in this virtual machine, which is just proprietary to this virtualized environment, that I want to use protocol number 1, and protocol number 1 is ICMP. That's what's happening here. So we'll go ahead and do a trace, and due to the magic of having numbers that are all lined up, the first hop Let's take a look real quick. The first hop says PC1 was my default gateway 10.0.1.1, which is router 1's address, because the last octet matches the router number. No accident there. Then the next hop is router 3. And then the next hop is router 4. And then it went finally to PC4. So 1, 3, 4, 10. Yeah, I see that. And I also don't like it. Let me share with you why I don't like that very much. Let's go back to our topology. This says that our path, and I'll use a different color here. I'll use green for the path. It went like this, 1, 3, 4, and then finally to this PC. So it used this path. Now, this link right here, and I'll put this in black, this is fast Ethernet. And all the other interfaces in the network for the routers, they're all gigs. So gig here, gig here, gig here, gig here. And so if we look at the costs, the default cost on a gigabit interface for, oh, I know what happened. Yeah, it's the problem I talked about earlier. So unfortunately, because the auto cost reference bandwidth is set to 100 megabits per second, basically it means that the fast Ethernet looks like a cost of 1, and the gigabit Ethernet also looks like a cost of 1. And so OSPF, as brilliant as it is with the default configuration in the Cisco environment, thinks that the cost to go to this network right here, to the 10.04 network is, and I'll put these in kind of a pink color here. The exit cost here was 1, and the exit cost here is 1, and the exit cost here is 1, so it's 3. And it sees this top path as an exit cost here of 1, exit cost here of 1, and wouldn't this be an exit cost here of 1 also? What's going on? I'm actually very curious now why that chose that path and not the other. Let's take a look. Let's go ask it. Part of the troubleshooting is, okay, so if the fast Ethernet is being treated like gigabit, still, why did it use this path? So let's go to R1 and let's ask it about the route to 10.04 and just take a look at what its decision points are in getting there. And then we'll fix the auto cost reference bandwidth to make the fast Ethernet look like a cost of 10 and make the gigabit look like a cost of 1. So let me go ahead and clear that off. And let's go take a look at R1. All right, I am actually very curious. I wasn't expecting him to use that. I mean, I can see why he might use that path, but why did he use show IP route, OSPF. Here are OSPF learned routes. 10.04, he has one path. He has one path to 10.04. Okay, so okay, time to get in the mind of Keith. There should be 2 routes there. There should be 2 routes, because if router 1 saw the cost going through the bottom path as a cost of 3, which it does, by the way, it's right here. This is the number I'm looking at right here. This equates to the egress interface costs as it goes out of R1, out of R3, out of R4. So the cost is 3, but my question is, why didn't it also see an equal cost route going through the upper path? And that upper path is right here. So I would expect that the cost going this way, I'll use a different color. Excuse me for a moment. Let's go ahead and use, how about that color? I would expect the cost going this way to be a cost of 3. And until we fix the fast Ethernet mistake there, that also a cost of 3. Let's just count them up real quick. So from R1's perspective, a cost of 1, 2, and 3. Yeah, and this path would be cost of 1, 2, and 3. Oh, yeah. So we should have 2, because that's what OSPF does, and many other routing protocols too. If there's 2 equal cost paths where the metric is the same, for the same exact network, there should be 2 paths, but there isn't. So let's do this for... So now Keith is going... Keith, talking about the third person. Let's solve one problem at a time. Let's first of all solve the problem where OSPF believes that every interface, gig and fast Ethernet, is only a cost of 1. Let's fix that first. So let's take a peek at R4 And this link right here on the bottom, this is actually fast Ethernet, and everything else is gigabit. So let's take a look at R4 and verify that, then we'll fix it. So I promised a little troubleshooting today. You got it. So go to R4, and on R4 we'll just show IP OSPF interface brief. Yeah, sure enough. So the fast Ethernet has a cost of 1, and the gigabit has a cost of 1, and that is because of this factor right here, show IP OSPF, and a space bar. It's because of this bad boy right there. The reference bandwidth is 100. So anything faster than 100 megabits per second is also going to have a cost of 1. That includes 10 gig, 40 gig, etc. So to solve that, what we're going to do is get out Notepad again and go into configuration mode. And let's do it on one, and then I'll copy it on the others. We're going to go into configuration mode and go into router configuration for OSPF, same process ID, and specify auto-cost, reference bandwidth, and then put a bigger value as a reference than the 100 megabits per second. So it's done in megabits per second. Let's go for, instead of 100, I'm going to add one more 0 and make it 1,000. Press enter. And now it's saying, hey, please make sure you do this consistently across all your other devices. So I'm going to go ahead and copy that and go to Notepad, config T, router OSPF1, paste, end, and then I'll do a show IP OSPF interface brief. That'll save me that typing. All right, so I'm just going to do that for all the rest. Copy. And this guy is already done. 4 is done, so I'll go to 1, auto cost reference bandwidth. Boom. R2, auto cost reference bandwidth. 3, auto cost reference bandwidth. And although I did it on 4 already, oh, check it out. So on R3, look at that. It has a fast Ethernet interface. It now sees it as a cost of 10. Perfect. We've now solved the problem. Now, what I would expect is that if we went back to our topology, that this path here going, we'll call it path B. This is path B. I would expect that path B would be a cost of 1. And this is now fast Ethernet, so that's going to be a cost of 10. And out here, oh, that's gigabit, so that'd be a cost of 1. So the cost should be 10, 11, it should be 12. Well, the cost of the high road here should be a cost of 1 here, and 1 there, which would be a cost of 3. So OSPF, when it sees those two paths, should choose path A every time, and path B should not even make it to the routing table because it's not an equal cost path. So let's go check and let's go see what happened. So we fixed the auto cost reference bandwidth challenge. Let's go back to our lab. Let's go back to our PC1. Let's hit the up arrow key and do that same ping. Okay, and we had a timeout on the 4th one. I'm going to do that again. Hit the up arrow key. All right, so we have the same path, 1, 3, 4, 10. I got to be careful what we ask for because I said I said there would be some troubleshooting. Okay, so PC1, so R1 is not using this top path at all to get over there. And so to troubleshoot this, what I would do first is I would say, let's troubleshoot the neighborships. Let's start at R4 and make sure R4 is a neighbor with R2. And then we can go to R2, make sure R2 is a neighbor with R1. Because if any of those are misconfigured or if there's a broken link, that would explain why this path isn't being used. So let's go to R4 and check them out. So here we are on router 4. Show IP OSPF neighbors. So R4 going up to R2 is fully adjacent, meaning we're sharing everything, and that R2 is a backup designated router, which means we're the designated router. So there's no problem there. Let's go to R3. Oh, I take it back. Let me look at my topology. Let's go to R2 and verify the neighborship between R2 and R1. Alrighty, so R2, make sure I'm on the right device. Show IP OSPF interface brief. So I've got OSPF on all 3 interfaces, and it's gig 20 that goes over to the router. So we could do a show CDP neighbors just to verify, basic. So my local interface, gig 20, oh, it's going to the switch. You know, some days it just gets like that. So the challenge here is just in identifying basic connectivity is that because R2 is connected to a switch, as far as CDP is concerned, and it's a Cisco switch, it's going to just tell us about that connectivity to the switch. It doesn't give us connectivity directly over to R1 because that's not our directly connected neighbor from a physical perspective. It's the switch. So we can still solve this. So we are connected to port. I'm going to document this as we go. So from R2's perspective, on our local gig 20, we are connected to the switch on its port gig 20. So let me go and update my documentation here. Let me add a layer. Documentation is, or can be, our best friend. So on the switch, this is port 2/0. And let's also verify that R1 is connected also to the switch. That'd be a good test. So we'll go over to R1 and show IP. Let's just show CDP neighbor. Yeah, okay, so on router 1, its local gig 1/0 is connected to the switch on gig 1/0. So let's document that as well. Oh, that was easy. Okay, so it's 1/0 on the router, 1/0 on the switch. On router 2, it's 20 and 20. Sounds like somebody was thinking ahead there as far as training purposes. And let's do a show IP Ospf interface brief. Make sure that we have on gig 1/0 Ospf running. And over on R2, if we do a show IP Ospf interface brief, make sure we have Ospf running there, which we do. Oh, look at this. They both think they're DRs. Oh, and we have no neighbors. Oh, yeah. There we go. So R1 and R2 both believe they're the designated router, and they don't see each other. So if we do a show CDP neighbors, oh, sorry, I have CDP on the brain. If we do a show IP Ospf neighbors, we have a neighborship to R4, but we do not have a neighborship with R1. And if we go to R1 and do a show IP Ospf neighbors, yep, R1 is a neighbor with R3, but it's not a neighbor with R2. All right, so we have a we have a problem. Houston, we have a problem. So they can't see each other. So the network Ethernet's broadcast from an OSPF perspective. So they're going to be saying multicasts, and they should be able to see each other's multicast. Let's try a ping from R1 to R2, and if that doesn't work, we'll continue the troubleshooting. So here on R1, the IP address of R2, it is 10.0.12.2. Okay, all right. I'm doing a Control-Shift-6. Just, I came too late. Anyway, I was going to stop the ping. No connectivity. So let's go check the switch. So on this switch, these two ports, 1.0 and 2.0, should be in the same VLAN if we want R1 and R2 to form an adjacency with each other. They have to be on the same network segment from a layer 2 perspective as well as a layer 3 perspective for the OSPF part. Let's go check out the switch. So on the switch, we will go to the core switch and, oh, well, spanning tree's running. That's handy. Let's do a show VLAN brief. And there's your problem right there. So gig 1/0, which goes to R1, is in VLAN 10. And gig 2/0, which goes to switch 2, or router 2, is in VLAN 20. So we could either move them both to VLAN 1, or we could simply move one of those ports to VLAN 10, or just put it in the same VLAN is the answer to that. Let's go ahead and take VLAN port gig 2.0 and put it into VLAN 10. And that way they can be in the same VLAN. So configuration mode, interface gig 2/0, switch port mode, it's already an access port. Switch port access, VLAN 10, verify our work with the show VLAN brief. Okay, they're both there. And let's do a show spanning tree for VLAN 10, just to make sure they're both forwarding. All right, and so this edge means we have port fast enabled. Otherwise, it may take 30 seconds or something close to that for the forwarding to happen. So now that we have layer 2 connectivity for router 1 and router 2 through the switch, let's go ahead and verify that we have connectivity. So we'll go back to the lab. We'll go back to R1. Okay, that's a very good sign. So they found each other. Now that they can see each other's hellos, they then went through the steps of becoming fully adjacent, which involved them sharing and making sure they had the latest and greatest updated copies of their databases, of their link states. And if we do a show IP Ospf interface brief, oh, look at this. So router 1 on gig 1/0 is the BDR. And because they just came together, you can't have two DRs. And router 2 had either a better priority on the interface or it simply had the higher router ID, which would be the tiebreaker. All right, so now if we go back to this client, PC1, and we do a trace to 10.0.4.10. This is PC1, this guy right here, going to PC4. The cost through this top path should be a cost of 3. And the cost through the bottom path, which is so high it's not even in the routing table, won't be used and won't even be in the routing table. In fact, we can verify that on R1. If we do a show IP route, and let's go ahead and put in 10.0.4.0. This is basically saying the details for that route is that the egress interface, last update from 10.12.0.2. What am I looking at? Oh, my brain. It's been a very, very long day. Let me take a look at the let's show IP route OSPF. 10.0.4. What? Oh, because it was going out the top interface. I was like, why is it going out the top interface? Why is it going out the top interface? That's because that's where the route is the best. And that's why when we were looking at the details for the route here, and it was showing that the egress interface was going to be on gig 1/0, I was like, what? That's how it should be. That's the better path. Also, if you notice that the route with the next hop of, the route for 10.0.4 with the next hop of R3 doesn't exist. It did not make it into the routing table because the routing table only likes winners. It's the best route. And if it's not the best route, it doesn't make it into the routing table. And as a result, that's why we see the winner here. All right, so I think we did it. I think that's everything. Let's go ahead and just verify from R1's perspective that we can do some ping. So if we do, actually we can do some traces from here too. So if we do a trace, and let's go ahead and do a trace. Let's see here, 10.0.4.10 space, and we can use the source option here. Now, let me tell you what the benefit is of the source option. The benefit of using a source is that we can mimic what it would be like coming from the PC. So when R1 pings this IP address or traces to it, it's going to use by default as a starting point the interface closest to that based on its routing table. If we say source it from 00 or from the IP address here on this interface, we then have a more accurate picture of what that traffic flow would be like if it's coming in from a PC. So that's why I'm going to simply add the source option there. So let's go back to the interface, and we'll say source, and we'll say a lot of options. Gig 00 is what I want. We could also plug in an IP address. So there's our trace, and I'll do that one more time. There we go. So the first hop was R2, and then R4, and then the client at .10. Wonderful. All right, so our objective, let me go back and make sure I look at our objectives here. Our objectives were, and I had a lot of fun, by the way. Thanks for going through that with me. Objectives were to plan, configure, and verify OSPF and do troubleshooting along the way. So the challenges that we faced were that the auto cost reference bandwidth was by default 100 megabits per second. So gigabit links didn't look any better than fast Ethernet until we went across the whole board in router config and told them so. We had a problem with R1 and R2 being able to see each other. They weren't in the same VLAN, so they couldn't form a neighborship. But once we did, they were great. Other things that could cause problems would be if there's a mask difference, like one side believes it's a 25-bit mask and the other side believes it's a 24-bit mask, they're not going to work. If the authentication doesn't match, they're not going to work. If the timers don't match, it's not going to work. If one side believes there should be a designated router and the other side believes there should be no designated router, like network or non-broadcast type versus a point-to-point, They won't become neighbors. So those all have to agree. So I want to thank you all for joining me for this OSPF configure and verify session. Also, I had an idea I'd like to run by you, and I think it's going to be great, and I'd like some ideas on a name for it. I'm building out the CCNA playlist. Every week we have 2 or 3 new videos or live streams that go into it. Hope you're enjoying that. Tell your friends, subscribe, hit the alert bell, have a party, be here with us, enjoy, study, and grow. Eventually those are going to be... So I do Sundays, CCNA Sunday, Subnet Saturday, and also a live stream on Wednesday, which we are right here. So at some point, the Subnetting Sunday or the Wednesdays are going to become, I'm going to have a full library in the playlist so you can enjoy the full thing. So here's what I was thinking. I was thinking of taking the topics from the live streams. So you go to the master playlist and go like dynamic ARP inspection or layer 2 trunking or router on a stick, or inter-VLAN routing with a multi-layer switch, or OSPF, or whatever it is, and those various topics, and taking each one of those and then having a challenge that somebody meant. The reason I got this idea was somebody mentioned a channel, a YouTube channel, where you just watch old people try to do stuff like me. And that's literally where I got the idea. I was like, well, yeah, let me do this. I would love to, your ideas on this is getting a topic from something we've done in a live stream where I've elaborated on it and gone through it and use it as a challenge for, maybe call it packet tracer panic or the rushed networker or something like that. And what we would do is, based on the topic that you would give me, I would go ahead and do a live stream of like 15 minutes, and 10 of that would be my time limit to design and implement and verify the solution or the technology that is recommended by you. And it'd all be CCNA level stuff that I've done in the live streams. So I think it would be a hoot because not only, let's pick, let's say we just did OSPF, so that's on my brain. Let's do spanning tree or something like that, or port fast or port security. So give me a topic, and then basically from nothing, like with packet tracer, building the whole topology, thinking about it for a few moments, and then in 10 minutes, building the whole topology, implementing it and verifying it, and then hit the stop button, like a 10-minute limit. I think it'd be great because that way it could be like a series that we could all check in together. It'd be a lot of fun. Get your recommendations. You could grade me at the end, like, okay, on a scale of 1 to 10, how did you do? Like, oh, total fail. Couldn't get dynamic ARP inspection working or whatever it is. But the time would be the critical thing because that's so fun. To set a timer, I could put the timer on the screen as well and just go at it. So take the topic that's been recommended, set it up logically, tell you what I'm going to do, and then from nothing, just take packet tracer, drop in the devices, drop in the configs, configure it, and I would just talk through it as I'm doing it, and that would help reinforce it. So that way people are, when they've been studying various topics, like routing or switching or whatever it might be, it'd be a nice, concise 10 to 15 minute way to do a refresher on it from soup to dessert. And everybody watching could do it themselves. You can say, oh, Keith's topics today is so-so. And just as you watch the live stream, get out packet tracer and boom, boom, boom. Oh, I didn't know you could do that. Oh, you could do that. So that's my thoughts. If you think that's something that is worth pursuing, I'm excited about it. I need 2 pieces of help though, if you'd help me. One is I need a name. I thought packet tracer pandemonium or something like that. Something that implies, hey, this is a 10-minute window for Keith to build and configure and verify some technology he's covered in one of his streams. The second thing I would need is a topic. And so if you would, not in the live stream topics because sometimes those aren't available after the fact. It depends on what button I click. But if you could, once this video is live, or if you're watching it later, the recording that is, if you could chat in a recommendation or 2 on the technology, something we've done in the live stream. You just go to my master playlist, look at the playlist, and say, oh, this topic. That'd be great. And so what I'll do is I'll just pick one. And as I start that series, I'll do it weekly. I'll pick one, and then I can go ahead and just demo it and have a lot of fun. I think it'll be a good reinforcement for those topics for everybody who's watching. Also, it'll be a lot of fun because I will not be able to get it all done in 10 minutes every time. And but I will try my darndest to do it, and then we can see how I succeed or fail under pressure, which is it's fun to see. All right, so that's it for this live stream on configuring, verifying, configuring and verifying OSPF. I've enjoyed having you. The next live stream is coming up in just a couple days. That would be Subnet Saturdays. That's going to a playlist followed by a CCNA Sunday, and then we'll come back to this Wednesday. As soon as I get those recommendations, I would love to start that for the pushy packet or whatever we're going to call it. Also, if you come up with a title for this series and I use it, I would be happy to send you an original Gangster of IT shirt, a theme shirt like Mr. Sloth is. Where is he at? There. That he's wearing. Just let me know your size. So again, your recommendations on the name and the topics would be great. And the person who picks a name that I end up using for that series, you've got it. All right. Thanks, everybody. Let me find some exit music. Here it is. And I'll see you in the next stream. Don't forget to subscribe, like, and study hard. Bye, everybody.
Life is a winding road, no telling where it goes. Driving through days and nights, won't stop for traffic lights. And I really wanna know if I'll ever figure out where the road goes. Even if I'm falling down, I will keep on searching for my highs. You can say I lost my mind, I will keep on holding my head high. Even if the sky is falling down. Jumping from cliffs so high, trusting our wings to fly. Sometimes we're crashing down, but we get up and start from the ground. And I really wanna know if I'll ever figure out where the road goes. Even if I'm falling down, I will keep on searching for my highs. You can say I lost my mind, I will keep on holding my head high. Even if the sky is falling down, even if the sky is falling down, yeah. The sky is falling down. Even if the sky is falling down.